Thank you for coming here and listening to me today. I'm Annapurni Subramaniam, so I just talking to people here, so realized that I should talk a little bit about the Indian Institute of Astrophysics, which I come from. So I'm the director of this place, Indian Institute of Astrophysics. It is the headquarters of this institute is right here, a few kilometers from here. It's in Koramangala, and that's a very small campus actually. And we have campuses right across the country. We have a huge campus in Kodaikanal, which is operational from 1895 onwards. So it's a more than 125 years old campus. Then we have a campus in Kavalur, which is called the Venu Bapu Observatory, if anyone of you know about it. It's near Vellore. It was established in 1960s. It has several telescopes. It's for nighttime astronomy, of course. And we established a center in Ladakh, which is in the Union Territory of Ladakh, and it is in Hanle, and it is at 4,500 meters above sea level, half the height of the Everest. And we operate, we have a 2-meter telescope. We operate remotely from a campus in Hosakote. And we also, so this is our USP, we build and operate ground-based telescopes, optical and also radio. We also build space payloads, and we have, the Institute has contributed significantly to the AstroSat Indian Space Observatory. And we are right now integrating a payload to be launched to study the sun, Aditya L1 mission. And I'm also proposing a next mission to move forward based on the experience gained from AstroSat. So this is the kind of expertise we have in the Institute. And I have extensively worked on ground-based telescopes as well as space-based telescopes. So from that experience, though I have not literally worked on building the James Webb Telescope, but I'll be using it, and I've already started using the data from it. So, so I think I can talk to you about how I feel about JWST and what excites me, and what are the important things I think are very niche and special about this particular space telescope. So I don't think I need to say what this image is like. This has been, I mean, a lot of this, the first light images released actually kind of captured everyone's imagination. And this is one of the images where there are a lot of things to talk about. And if you look at social media, people have been reacting extremely various things on this actually itself. And it's not only just about pretty pictures. Pretty pictures excite people, but there's a huge amount of cutting-edge science going on there, using a cutting-edge instrument. So I'm here to convey to you what is so special about it and what we expect to know from it. So, I started off with ground-based astronomy. Since the time of Galileo Galilei pointed a telescope to the sky, we have been using and establishing a large number of ground-based telescopes across the world. And today, thousands of ground-based telescopes operate across the globe, with astronomers capturing new views of the universe, new knowledge every day, every night. And ground-based telescopes have long been the workhorses of astronomical research. And this particular picture you see here is the night sky of our Hanle Observatory. And this is a picture taken from an SLR camera. The telescope is out there. There's a 2-meter telescope. This has got one of the darkest skies in the whole world. And this basically because it's quite, altitude is high, and also there's hardly any moisture in the sky. So it's a high altitude desert. So you are very little obscured by the night sky as such. So it is the nighttime, it's like a magic. So many millions of stars just appear out of nowhere. And we are trying to preserve this night sky by declaring this as the first dark sky reserve of the country. So we are working with the administration of UT Ladakh and the local community to help them to develop it, as well as to use astro-tourism, etc., to benefit their economy as well. So this is besides the point. So moving on, what are the advantages and risks of ground-based telescopes to a space-based telescope? Compared to space-based telescopes, ground-based telescopes have much to offer. They can be built bigger and for less money. They are easier to maintain and upgrade. You can always go and tinker with it if something is not working and change it. Change an instrument, a part is not working well, you can always go back and repair it, etc. Practically speaking, they have also much lower risk of being damaged by radiation, malfunction, and space debris. And this era of so many things out there in the sky, everything, so many things around the Earth, going around the Earth, so debris are increasing actually. So while ground-based telescopes are generally placed in isolated, elevated locations, just like the one you saw of the previous one, with little light pollution, they still face the challenge of atmospheric distortion. So it's only in the Hanle region you get this, but then there are other places where you have telescopes as well. So every night you point the telescope to the sky and take data that needs to be corrected for the atmosphere that is present at that time. So you have to have corrections applied, otherwise the data is useless. So this is very important in the case of ground telescopes. But increasingly, scientists and engineers are turning to space as a new frontier for advanced telescopes. Space also offers another thing which I will come to later. So the trend is to have space telescopes since 1960s, and also we have used balloons to carry certain instruments up to a higher atmosphere and stay there for some time and take the data. So that is also being used. So the goal is to get a sharper view. So you actually can beat the atmosphere and get a sharper view. So why do we need space telescopes? Two things. One, you don't want to get disturbed by the atmosphere. You don't want the night to be clouded out because there is clouds in the sky. And also you have, everyday experiences, you can see the rising sun, the setting sun. You cannot look at the sun when it is at noon overhead. The simple reason being the sun is not getting dimmer in the morning or evening. The thing is, the dimming is done by the atmosphere. And you also can see that it's not only the dimming, it's reddened. So there's a certain amount of light which is absorbed. The blue is absorbed more than the red. So your eye is able to capture the red more. So these corrections have to be applied on daily basis for each and every data you collect. So it becomes painful. The second thing is, as life is flourishing on Earth, one of the main reasons is that the atmosphere is able to stop the high energy radiation, which is harmful for the living organisms. So if you can see this part, which is basically the high energy radiation is actually stopped by the atmosphere. So we cannot collect it on the ground. So if you want to collect the X-ray which is coming from the sun, or UV coming from the sun, ultraviolet coming from the sun, it doesn't reach the ground. But that doesn't mean that none of them out there are emitting in these wavelengths. So if you want to capture them, you need to get your instrument up above the atmosphere. So the space allows you to expand your reach beyond the visible part which our eye can see and which can be captured on the ground. So that is for the high energy radiation. Now, what happens when you go to longer wavelengths where the radiation is much less, with lesser energy? So there also you have obscuration, very big obscuration in the infrared. So this is the infrared region. And you have peaks here, particularly because of the water vapor in the atmosphere. And then there are blocks out here. So, and then the radio wavelengths, which is actually quite, it's transparent. So if you want to cover the entire wavelength range to study the various phenomena which is happening in the universe, you need to have a combination of ground and space, or only the space. So space you cannot escape. You need to have telescopes in space to cover the wavelength range or the electromagnetic spectrum range. So the seeing, which is, as I already mentioned, the disturbance which is caused by the atmosphere blurs the image. So if you want to get it sharper, you have to beat it. There are certain technology like the adaptive optics, etc. available, but then still it is quite cumbersome. So keeping that in mind, the Great Observatories program led to the creation of 4 big powerful space telescopes. And these are the ones, this is the Compton experiment, the Gamma Ray Observatory, This is the Chandra, this is the gamma ray region, this is the Chandra X-ray Observatory, this is the Hubble Space Telescope, and this is the Spitzer telescope. So Spitzer is in the infrared, the Hubble Space Telescope is in the visible light, this is the X-ray and the gamma ray. So they covered a huge range, and all of them space telescopes. So the things which you can see is that the phenomena like the supernova remnant can emit in multiple wavelengths, and there is a probing the physics of various types of emission mechanisms happening there. So if you look at it only in one wavelength, you will not understand the entire physics which is going on in that particular region. So these are the ones which are launched. The most important one being, this happened between 1990 to 2003. The Hubble Space Telescope started in 1990, and then it kept going on now, and it's still going on. And it's really amazing. So it has contributed to 3 decades, and particularly because it is nearby, actually, I'll come to where it is located. There are space missions which actually go there and do the repair. So because of that, we are being able to replace and the damage or change the instruments and add newer technology instruments out there. It's just like your backyard where you can actually go and do it. But because you could run or you could do the spacewalks and the change of instruments, Hubble is still working. These are these are phased out actually, and but they contributed extensively to our understanding of the universe in various wavelengths. Now, why do you want to have various wavelengths? It's just a picture of a galaxy where you can see that the shape and the size and the kind of things which is tracing, depending upon the temperature, it changes. So if you look at the same galaxy in X-ray, which is actually tracing a very hot gas, the distribution of the hot gas is different. And if you look at ultraviolet, which is basically tracing very young stars, where the stars are being formed, it actually delineates the spiral arms. But if you come to optical, you start seeing everything together, like the stars, the dust, the obscuring places where the stars are being born, and some emissions. But if you go to infrared, it is a cooler one, so it starts seeing quite a bit of warm dust, old stars, etc. So what I'm trying to say is that the universe is full of stuff which can emit in various wavelengths. So depending upon which wavelength or which kind of a region you want to probe, it gives to different physics about it. But you need a coverage of the entire thing to study what all things are present in galaxy. Just because you got one very good image in one wavelength does not tell you the entire story of that particular galaxy. So this is the realization we have got after these, operating these telescopes, and the radio, which is actually looking at the gas, which is actually the hydrogen gas. So this combined tells you that where exactly the galaxy is holding the gas, where the stars are able to form, where it is able to ionize the gas, and if you have a very hot center, is it a black hole sitting there? So different types of activities going on, physics behind all these activities can be probed only if you combine all these wavelengths. Same thing with the stars. So stars can be, so this is a very famous diagram where you plot the brightness of the stars versus temperature, except that the temperature is hotter here and it is cooler here. So our sun is somewhere here. The stars which are less massive than the sun becomes cooler than the sun, and anything hotter than the sun becomes, or rather brighter than the sun, are also hotter. So if you want to study the hotter stars, you have to look at the the ultraviolet. And if you want to look at these cooler stars and study planet formation, you have to look at the longer wavelength, which is the longer wavelength. So this region you have to look at. So depending upon the temperature of that particular object, you need to choose, like if you want to, for example, if you want to find out whether the people are there in this particular auditorium, can you do that by taking a picture? Yes, you can, because we are emitting in a particular temperature. So if you have a camera which is sensitive to that particular temperature, that wavelength, you can take a picture. This is the same reason why infrared cameras were prohibited to be imported from US. They wouldn't give anybody that camera, because using infrared, you can actually trace army moving. So these are directly coming from defense applications as well. So basically, infrared cameras are used to trace living organisms or movement of army. So infrared cameras are the ones which are also powering the James Webb. So, or capturing the images of the universe in the infrared. Now, why do you want infrared? I'll come to it. So before going ahead, these space probes also helped you to look back in time to find out when did the galaxies form stars? Are all the galaxies like our own Milky Way? When did they form? When did they merge? Now we know that our galaxy has eaten so many nearby galaxies. When does it happen? And what happens when you keep eating the galaxies that become no more stars to form? So does it happen to our galaxy? So these kind of questions you need to understand. You need to look at other galaxies and which are back in time. Then only you will understand that, right? So looking back in time tells you so many things. So giving you an overall things about the landscape, these are the kind of different space telescope out there, and these are the different types of ground telescopes. So these are in different wavelengths, all right? So if you have these missions, where do you put them? Can you actually position and just station it out there? No, it's not possible. It'll just fall back onto the Earth. So it has to orbit the Earth. So these orbits are of various types. Now, what are the kind of orbits you have? One is the low Earth orbit, which are kind of a few 100 kilometers. So Hubble Space Telescope is out there. So the Indian Space Observatory, AstroSat, the first Indian space observatory, is at 650 kilometers. So that is the low Earth orbit. Now you also can have, this is equatorial orbit, which is going very close to the equator. You can also have the similar polar orbit at the same height. But in between, you can also have little away, you can also have the geosynchronous orbits. But the ones which we'll be talking about today are different. They are very, very far away, 1.5 million kilometer. This is the L2. So now if you have two bodies which are, it's like a binary, two massive objects, there are places where, like this L1, this is actually equally attracted by this and this, right? So the advantage of this is that if you put a point mass out there, it's more or less stable. And not only that, when this thing moves around, this point moves along with it. So you don't have to literally propel yourself and move along with it. You can actually move along with it. So that's very cool about it. And if you can place a mission here or payload here, which can actually always face the sun. It will not get obscured at all. So if this particular Earth goes over here, the L1 goes over here, so it will be always in between sun and the Earth. So solar missions which ISRO will be launching, Aditya L1, will be here. So if this goes around, the L1 will be here. If the Earth comes here, the L1 will be here. So it will always be in the front. And L2 is always at the shadow of the Earth. You can imagine that, right? So it will always be blocking the light from the sun. So it gives you nighttime access all the time. So many observatories are placed here which requires to look at the night sky. So JWST is going there, has gone there and is making an orbit around it. So that is how the orbit of the JWST is. So these are the overall orbits which various kind of spacecraft use. So what is JWST? So this is the overall, I'll come to the individual mirrors. This is a multi-mirror telescope. This is the first multi-mirror telescope in the sky. We have multi-mirror telescopes on ground, but this is the first one in the sky. And this has got different instruments which can look at it, but you can see that all are infrared. So it is not covering, unlike I talked about all the electromagnetic spectrum, right from the gamma rays to, it's not covering everything, it's just covering the infrared. That is the reason why it is using looking at only the infrared. So this is the final picture which we saw from ground before we said bye-bye. So the camera captured this one, and then I'll tell you what happened to it. So this launched on 25th December, and this is not exactly the next generation when it comes to Hubble Space Telescope, because Hubble Space Telescope had a ultraviolet and optical part. But this is more in the infrared. But this is the next generation of the space telescopes. In that sense, is the next one to Hubble. But it is looking at a different wavelength. So it is actually the next to the Spitzer. Spitzer looked at the infrared. So we compare, when you look at, people compare Hubble to James Webb telescopes. It's slightly different because the wavelengths are different. But this is the Spitzer's next generation. So how does it work? You cannot, this is the picture, you see it, you cannot launch it like this. So it is folded and launched. And when you actually launch it, this goes into it is stored away like this, and then it is put it on the top end, and then you have this propellants and the booster which is coming onto the rocket. So the rocket part, this is going into this part. So you can see that this is folded in and towed in. So you have to unfold everything and work like a telescope. So here you have mirrors. It's nothing, it's very, very fragile stuff. You have to make sure that the mirrors reach the destination without being broken. And the mirrors are not sitting in the, if it's a mirror, it's not sitting in this place so that the shaking is low. It's actually looking at, it's stored this way, vertically, not horizontally. So all the more vibration goes into it. So the most important difference between putting up an instrument, whether it's an optical wavelength, in the ground and in space, is that it has to withstand all the jerks it'll face during the launch, and also the thermal variations it'll face. So one goes through the test, something called, people generally call it as shake and bake. So you have to shake all this and prove that it doesn't break. It'll withstand all the gravity when you launch. And also all the deployable mechanisms have to be tested multiple times, because there are a lot of deployment over here. And the deployment has to work. You cannot say that I don't know what happens, because you're just commanding here, and you should know that it worked. So you should also get a feedback to confirm that it worked. So it's like you have an instrument, it's sitting somewhere else, and then you're sitting here and guessing that it is working. If you're not getting a signal, you can go to the other room and check what happened to it. Now you can't. So you have to multiply make sure that it is working beyond doubt. So redundancy is extremely important. If something doesn't work, so risk management and planning, and to make sure that zero failure is extremely important here. So system engineering for any missions are huge. It goes through several reviews, several tests. If it fails, it goes back to ground zero. It starts all over again. The entire process has to be reviewed, tested, and made sure that it works. So delays are very common, because something doesn't work, you're one step back, or maybe 5 steps back. So if you hear about any mission it's getting delayed, these are the reasons, because you have to make sure that it goes up there and works the way you wanted it, and you can't take chances. And so these are there are many. I encourage you to go through the YouTube. There are lots and lots of videos of all this engineering stuff. I'm not going to show you here. There are plenty of them. They're wonderful. They're really beautiful. And this is an engineering marvel. Everything has gone through it. Like starting from what is the material of this mirror, why it was taken, how it is made, what is the accuracy needed. And you can see that these are gold-coated mirrors. So why do you want this? How do you put all these mirrors together? So this is absolutely brilliant, starting from each and every aspect of it. And you can see here that this is the huge chamber in which the whole thing is going to go. So before putting it, each and every component is tested and made sure that it can withstand the shake and bake. Okay. On top of that, after integration, because integrating you have torqued bowls, etc., right? Those are critical aspects. These torqued bowls, everything can come off. So it has to be again tested everything together. So this is a huge baking chamber. It goes inside and gets baked. So several tests have to be performed before that. And this is the stored away. So you can see that this particular 3 mirrors are already folded. So this also gets folded, and this is stored like that, and once it is well deployed, this particular secondary mirror sitting here will come in the front like this. Otherwise, you just fold it away. So it has to be deployed. So this has to be, this is a deployment mechanism. It has to work. No way, if it doesn't work, that's it over. So like that, there are many single point failures that were identified in this mission. So once it is launched, you can see the sequence. There have been a lot of things which are done. So this carries fuel in it, and it has its own thrusters, and it uses those thrusters for course correction, as well as to go in that particular orbit I showed. So it carries fuel. So if the fuel is well managed and not used through this course correction up to the L2 point, it can actually stay for a longer period. You might have read now that it can actually operate for a longer duration. This is the reason, because the fuel over there has to be managed and used appropriately. So there are several things it goes through. The first and foremost is the solar array deployment, because you need power for operating everything. So here it is the solar power. So first the solar arrays come on and then start taking the solar radiation to get the solar power. And then that power is used to open this flaps, and these are actually the shields which actually stops it from the heat from coming over here. These are infrared detectors, I'll explain that. And slowly one by one it comes, and then finally it's over here. So it takes a long time for it to actually reach there and start going around the L2 point. So a whole series of observations. So you might have seen that it has got launched in December and nothing happened for 6 months. So what's it been doing? So these are all step-by-step process. So where does it go? To give you a scale, this is the Earth, this is the Hubble. Hubble, as I said, is very close by. That is the reason we could go there and do some repair as well. Now it has gone beyond Moon. It is at this point, L2. So it's very far away. It's quite far away, and it's cold, very cold. So because of that, the instruments actually can perform in infrared. If it is not cool, what happens is the camera will pick up the data from every thermal source around it. So it should not be picking up its own noise, but the signal. So for that, it has to be cooled down, and this is the ideal place. So how does it work? So it is going around, it's like going around, the Earth is going around, this is going in circles around it, and then again when the Earth is over there, it is on the other side. Again, Earth is there, it is going on the other side. So it's always be on the behind the Earth. And if you look at it in this way, I'm showing the orbit in this way for these pictures, and then I'm tilting it. So if you look at it, this is here and it is going like this. So it is going, why do you want this large orbit? Because the solar array which is behind this telescope has to get sun's rays for power. If I put it very close in a smaller orbit, the Earth is blocking it. So it will be like the permanent eclipse, solar eclipse. Then in which case the solar arrays will not get power. So it goes in a much larger orbit, and this orbit is quite big. I think it takes a few months for this orbit to complete. It very slowly goes around it. So when it is going around, after reaching this point, there are several things it goes around, like you have deployed the telescope. Now once you deploy the telescope, it is able to collect the light rays, and it has to go to the, during the orbit it takes a lot of corrections or deployment of the instrument. It's like this, you have your mobile phone. You want to take a photo, right? You switch on the mobile phone, so switching on is done. Now it has to switch on the cameras. So the camera switch on is also like, all your lenses and everything will be there. Detectors, etc. Now they're all parked at 0 voltage, etc. Now you have to power up everything and make sure that your positioning of the various lens system within or the optics within all have to be aligned and tested. So each and everything has to be powered on and tested. Now believe it is very far away, so you have to have all the commanding sent there, and then you have to get all the data back. Then only you can figure out whether something is actually happening, the correction which you wanted to do is happening or not. So in order to test each and every component to make sure that each and every component is working the way you want it, there would be so many diagnostics values you want. So apart from the data you get, pictures you see, there will be a lot of metadata which needs to be beamed down for the engineers to analyze the health. It's not only the beginning, continues to do so throughout the lifetime of the mission. Because that's the engineering data, that's the metadata, which is highly important to study the functioning and the health of the system. So these are the single point, I mean, there are many things which are said there. So this is the picture which is taken. Many people actually observed the JWST, which is launched, and you could see the thruster, the rocket going. Many people actually took the photograph. I could also take the photograph and see it. People didn't know it. Many people thought it's a comet, but it actually moved across the sky. So there are many single point failures, but it actually survived everything. Why do you think the single point failures are there? Statistically, if speaking, something should fail, right? But it is tested so much that the statistical occurrence is reduced. So that is the only way when you can say that, okay, you have planned for everything. So comparison between, I just wanted to put it because you would have seen comparison between Hubble and JWST all the time. So Hubble is a single mirror telescope. Spitzer was also single mirror. Now this is a 6.5 meter, it's a multi-mirror. Now why do you want a multi-mirror telescope? Why can't you go with a single mirror? There was a huge risk of creating a big 6.6 meter diameter, thin, one single mirror and sending it up there. So it is huge risk. And even on ground, when you go beyond 8 meter, you cannot hold one single mirror and make it work like a telescope. So the technology is to put multiple mirrors and make it work like a single telescope. The problem out here is that you have to make sure that all these segments act and support it so that it acts like a single meniscus. Now your systems which can actually move up and down or move laterally to make sure that it acts like a single mirror is highly complex. Not only that, you have to figure out mechanisms which can move hardware, which can move nanometer level. Even if someone claims that it can move nanometer level, you need to measure it. So it's not only about manufacturing, it's also about testing and calibrating. So India is actually partnered to a 30-meter telescope where the segmented 492 segments are going to be made, and the segment support assembly to make sure that all these are working together is done by the L&T in the country. So it's a very highly advanced technology. The same technology is used here for multi-segments here. And Hubble, one could go and do the repair. Here we can't because I told you it's very far away. It's impossible. Unless you bring the telescope back to Earth, repair it and put it back, which just actually doesn't make any sense. And Hubble had an issue, like the initial Hubble vision was quite distorted because the mirror which had the final figure was not the one they wanted. There was an inaccuracy in that. So they had to put a corrector in, and that was done, and then Hubble started functioning. But that is not possible in Webb. So this is, another thing is that the Hubble had a tube. So I think whenever you talk about a telescope, everybody kind of thinks to be a tube, right? That kind of thing comes to your mind, it's a tube. But here it is not a tube. There are two reasons for it. One is, it's infrared, and you want the entire thing to be cooled out. So if it is tube, there is a possibility that the heat gets trapped inside. So for it to cool, and it's quite a big aperture, so it's easy to, and you have a secondary mirror as well. So it's impossible to put a tube that big out there. But there is a price to be paid, it's open. So you would have seen that meteorite strikes on this mirrors are there, so there is a price which will come. But I mean, there's a hype in the media also that the mirrors are damaged and the JWST is damaged, etc. It's not like that. There's a small particle which comes and hits the surface of the mirror. What happens is the surface configuration gets altered a little bit. So that mirror's surface accuracy gets reduced. That does not mean it's not like a huge thing, a huge boulder coming and hitting it. It's particles. So this is, there are so many, I just put this no clarity here, you can't read anything, it doesn't matter. I just wanted to put it so that, all the engineering diagrams, like anything you make, here also you have plenty of engineering diagrams. So how does it work? You have plenty of mirrors out here. Each mirror, I'll tell you how it is aligned. But assume that this is the single mirror, primary mirror. This is a mirror. The beam of light is falling on it. And then the beam, you can see this beam coming here. And then the beam gets reflected out here. This is the secondary mirror, which is being held by here. So this light goes behind tertiary mirror. It comes back. There is a fine steering mirror here. So even though you have this light coming here and coming back, it's not actually quite well sharp. The sharp, because it's moving in the space also. So there's a drift. There's some kind of a blur. Everything will be there. But this fine steering mirror actually kinds of controls and makes sure that it is extremely sharp. It's on-board steering. So whenever there's a drift, what you do is you have a picture and then you have a star, you lock onto it. If there's any movement you see, that much of movement is actually, it's a closed loop mechanism. That shift is given to the shape. So it actually alters the thing. So by doing that in a certain frequency, you make sure that the images which are captured over here by this kind of cameras, the star stays in that same point. So in our observatory, like in AstroSat, we have a UV telescope. You will get a drifted image. In Hubble Space Telescope also, you get a drifted image. You correct the drift post when you bring down all the data down. So it's a post-processing. Here it is actually a online processing. It's a closed loop system. You can't beam down to ground and give it back. It's a closed loop system within this spacecraft itself. Its onboard computer takes care of it. And this is the whole space it sees, and the entire detector, you would have seen many detectors, near infrared, the mid infrared, etc. all see different parts of the sky. So you can actually do a multi-exposure. It's like you have a mobile with different cameras, which is actually looking, this picture is taken, this picture is taken. It's not, you can simultaneously operate it. So it's not like I operate one and switch off the other and then switch this off and switch it on. So which is actually not valuable use of this time in orbit. How much ever time you spend, you capture as much as possible. So that is the philosophy here. And the mirrors. So Hubble is single and this is so many mirrors, 18 mirrors are there. Now why hexagonal? These are some questions which I've heard from people. This is the way the best packing it can do. You can see that if you have a octagonal, it leaves a gap. If you have circles, of course it leaves a gap. So hexagon is like the honeycomb. So it's a closed packing thing. Now, when launching and deployment, it's not coming back to the exact point where you want it to be. So there's something called phasing one has to do. Phasing would mean that there are gaps, they're not aligned. So there could be gap, there could be non-alignment. So you have to shift it like this or move it like this. So both the piston movement and the lateral movement is possible using support system. So this is the heart of any segmented mirror telescope. So this is out there in space. Now, how do you align it? How do you know that it has to? What kind of commands do you give? So the point is that if all the mirrors are not aligned, everything will be beaming onto one point or one point, it's going like this, because it's not aligned. So you can see that if you take a picture from above, all the point source which has gone to different places. It's not going onto the same focus. It's focusing here, etc. You have to bring everything onto one single point. So one by one you move so that it actually comes back to the single point you get. So that is measured using this particular, it's basically like a point spread function. You will get multiple peaks. When you keep changing and aligning, this peak keeps increasing because the brightness at the center keeps increasing. You're bringing all the thing back. So you tilt it, and it takes a while to understand, but it's basically that by tilting, I make sure that the light goes to this particular secondary. So this is the heart of the thing, and you may be moving this also. It's not like once done forever. No. If you change the position and steering it another way, it can change. But the alteration you need to do is very minuscule. Not that much, but you have to do it. So that keeps happening in the web all the time. So all the instruments are behind here, and these are the different mirrors, different kind of instruments. So the near-infrared camera is given supplied by the University of Arizona. So I should also say that different components are very, very highly sophisticated. So all the things are not available in one place most of the time. So expertise in making something will be with some university, some center. So these are contributions from various organizations and various institutions where they have their own expertise. So you can see that is coming from, some are coming from ESA, some are coming from the US, some are from JPL, etc. And this particular thing, the fine guidance sensor, which I told you is very important to stabilize the image, is coming from Canadian Space Agency. So the mission is a collaboration between NASA, ESA, and Canadian Space CSA. So science diplomacy is an example of science diplomacy, because science actually brings nations together to do projects like this. So these are certain things where this particular shield, which you have seen here, covers and makes sure that it is a hot side is this side, and the 4-layer which is over there in the shield, make sure that this particular place is very cold, and one of the instruments required to be extremely cold. So this is how it works. So light from the sun is hitting on the other side. So each layer this is a space blanket, and they make sure that this stays cool. There are a lot of videos which actually explain how this is done. You can go and watch it. And the entire instrument suit is behind here. This is an integrated instrument suit. So all of them, most of them work at 37, and this one instrument is working at 7 Kelvin. This is using helium to cool it down. So this is the wavelength range. So some of them cover the optical. This is up to optical. So this is what visible is known. And this is the entire thing is. This is called the near infrared, and this is the mid infrared. So this part you can still access from ground. Not many water vapor blocking is there, but this region is completely blocked because of water vapor. And this is highly important for studying molecules. Molecular emissions and absorptions happen here, and particularly important for looking at star-forming regions or planet-forming regions, where what kind of molecules are present there. Even looking at a spectrum of the planet, surface of the planet, atmosphere planet, we could have seen water bands are already detected. So they are all sitting here. So this and the spectroscopy is extremely important to detect it. We are still waiting for many of these coronographic images which are coming from there. So first release images have been mostly on galaxies and deep space. The nearby universe images are still awaited, and many of the proposals from Indian PIs are also weighted in that. So this is to show that this is giving you spectrum. Spectrum is nothing but you look at an object and find out how much intensity is in each wavelength. So suddenly you see some wavelength intensity dipping, which would mean that some molecule absorbed it. So we are waiting for the signature, biosignatures or molecular signatures in spectroscopy. If anybody is interested, I'll discuss more about it, but it's more technical to understand what exactly this would mean and how you extract information about it, out of it. So this is what I was mentioning. This particular PAH, which stands for polyaromatic hydrocarbon, and silicate, these are particular grains which we know that they are present in the interstellar medium. So this PAH band traces where exactly these dust grains are present at very high resolution. So you need molecule to start with something. These molecules coagulate and build and bit more. So where are these molecules present? So these are the main drivers. And how are they placed? So these filters would mean that if you have an imaging which is beaming coming down, you have to place that particular round filter there. That's basically an optical cutout. So there the beam is taken. So you have to keep changing it. So it's a deployable mechanism. So you have to keep deploying and changing all this. And this image plane has a lot of deploying stuff there. So all this have to be tested one by one, and then when the images are obtained. So you would have seen this spikes in the mirror in images, right? So we'll also see in the first image itself, you see. So the reason behind it is that the spikes are coming from two things. One is the diffraction spikes coming from the hexagonal mirror edges. And two is the diffraction spike of this particular thing, that is the secondary holder. So this add up together, and you will also be curious to find out why some have spikes and some don't have spikes, right? So that's depending upon the amount of intensity. If you have too many, it's very intense, then you can see the spikes. If it is not, the object is not that bright, then the spikes are there, but the spikes are fainter. You will not be able to detect them. So the spikes will be an integral part because of the structure of the telescope. So the very important thing is, like, if somebody tells you that it's a JWST image and it's actually a Hubble image will have a cross. The JWST will have the signature. But at the same time, many of the first release images have removed this, they have modeled it and removed it, because this can actually flood the images. So you model it and remove it as well. So you can see this. So this is a model which is actually working. So if you know that you expect the spikes to be present in beyond certain brightness. So one can model it and take it out as well. So coming to images, these are the images taken based on certain ID. So even during commissioning, they had proposals, and the people who participated in the instrument building actually have got data, and they have these are some parts of the Large Magellanic Cloud, which is the nearby galaxy. So you can see that. Okay, one more thing which I should point out, that the color images, how do you get it? You can't see the sky in infrared, but when the images are made, what happens? This is actually the intensity which you record in that particular wavelength. Now, if you want to see it, you give it a false color image. So any astronomical picture you see is provided with a false color image, depending upon its intensity. So infrared, if I say that this is how it looks, you can't see it with your eye. So you have to depict that intensity distribution in a wavelength where your eye can see. So all are false color images. But that is how it looks in the different wavelength range. So this is a rider which will go with everything. So you have to understand how an astronomical image is rendered. Okay? So when you have to make a color image with multiple colors, you have to use multiple parts of the spectrum and co-add. You will see more of them in the next slides. So before that, so these are the two astronomers who have collaborated. We don't have any, directly I cannot apply in the first cycle to JWST, but you can apply through collaboration, through people who are already part of the web collaboration. So Jesse and Manoj are part of some of the collaborations, and they are working on stars which are being just formed. So they are working on that aspect, and their proposals are, actually one is observed, the other will go sometime. So this is one of the pictures which you have seen. So here you can see different colors, right? So red and blue, and so you can see this. Now you will know why this streak is coming over here. And these are red, but these is blue, etc. Right? So each filter, as I mentioned in that, each wavelength, you give a different color. So the intensity you have, you change the color of that particular filter. So you give, let's say, filter number 1, make it yellow. Filter number 2, you make it green. Filter number 3, you make it red. Now, in one filter, something would have been bright, and the other filter, it's not bright. So it will appear like a yellow, more yellow. If it has more red in it, it will appear more like red, right? So that is how the color is depicted over here. Now, this has a whole lot of stuff. You can see all these smudges, you can see various spiral arms, you can see some galaxies which are very, very red, which are very, very far away. So many scientific results have started coming just from the first release images. Now, these are the gravitational lensed galaxies. These actually are galaxies which look very nice looking galaxies, but they are getting distorted by the massive object in between. So astronomers used the the distortion which is happening to actually study the mass which is present in between, which is actually not detectable. So gravitational lensing, these lensed images are highly important to find out the mass which is in between, which is undetectable. And this is another picture which shows you that this is the object which actually gets lensed, because this light, it bends and comes here. This light also bends and comes here, but for us it looks as though it is coming from here and here. It actually is one galaxy. So it has been, we know it for a while now, and this is actually extensively used, and here you can use it all over to study the mass distribution. And the other one is looking back. So when the nearby galaxies, when they go far away, two things happen. They become smaller, and this pattern of wavelength emission, you can see it is centered out here. This pattern of emission keeps shifting to longer wavelength. It's like the Doppler shift, but not exactly like the Doppler shift. So this is actually called the redshift. And because of the redshift, the entire pattern of emission from the galaxy changes. So once you know the pattern and you trace the pattern in the infrared, you can see that this pattern from this is the visible light, it shifted to much longer wavelength. So it shifts to longer wavelength. So the more redder you go, you probably will be capturing the higher redshift galaxies. So if I'm observing only with Hubble, the only which is redshifted up to optical I'll be able to catch. But here you are able to catch up to infrared. So you're able to look back. So this is one of the important reasons why you're going for the infrared, because you can actually look back. And the reason why it is not like Doppler is everything else is stationary, only an object is moving towards you or far away from you. Like a train moving towards you or a train moving away from you, like the sirens you see. Everything else is stationary, but only that is moving. But here, everything is moving along with it. So it just the universe is expanding. So that gets stretched. So it's nothing special about it. Unlike Doppler, where it is special about between you and the object. It's not the same with you and another object. So the cosmological principle is actually the isotropy of it. And because of that, you get extended, and we get a table like this where you can equate equations and find out that at a particular redshift, how much is the look back time. So you can go up to 10, 11 in the case of Hubble, but if you want to hit more than that, you need to go to infrared. The same reason I said, because the pattern is shifting more towards the infrared, but sensitivity is important. So that's the reason you have to have bigger collecting area, so you can actually collect and look back. So that is what JWST is doing. And not only that, you have captured the data, and someone is sitting on the data. Will the word be able to do it in an analysis? Now everybody is doing the analysis and doing the studies, and everybody gets to know because the data is released. So all these space telescopes have this archive. So this archive lists out all the missions, and you get not only the data but also tools to analyze it. So it's very important for any observatory not only to capture the data but disseminate it to the public so they can start using it. So actually the data was released on 12th of July. Now the papers, if you see daily releases, flood. It's not only images flood, the papers are flooding. So people are working overnight, 2 days, paper is out. So you can see that this particular, this is a deep field. You're already seeing so many papers coming out already. This is just a number of days, or papers are more than that, the number of days. So many people are working. It's a huge group working with various types of data, looking at. These are all coming from the early universe, looking back in time, etc. So I wanted to say where India stands, India's mission stands. So this is the AstroSat, which was there in the ISRO, where before launching, this is the UV imaging telescopes, two here. And I was involved with the UV imaging telescope as I'm still the calibration scientist on this. And this was launched on 28 September 2015, and it is still in orbit. And it goes once in 90 minutes above Bangalore every time. So once in 90 minutes crosses Bangalore. It's been crossing. So these are the kind of tests we have. The lab in Hoskote, where we test everything, as I mentioned, right? The thermovac, which is the thermovac chamber where the telescope went for testing. So this is the different types of tests we have, and this is the telescope where this is integrated in the 2 tubes. Sorry, I think it's got a timer. So this is the shaker. So this is sitting on the shaking platform, and that is being shaked. So it has to survive everything before it is launched. And so this is one of the first images which we got very excited. There you can see the this particular image is taken from a previous NASA mission called Galaxy. You can see how coarse it is, and we got the images of the same object, and it's much, much better. So this revealed that this actually telescope can do wonders and is still working. It's working like much better than the previous UV mission. So India is also actually doing good job. It's not we don't publicize as much as the other one. So we have different types of images from the UVIT, and the Payload Operations Center is in Koramangala campus. This is the UVIT was integrated in our Hoskote campus, entire thing. So we have the entire facility for UV integration, and this is the payload. So now, what is next after in AstroSat? So you can see that the Chandra, Hubble, Webb, and there's the next one going up, Roman and Spitzer. There's no mission in the UV. They're all in the infrared. So now we have the capability in the UV, and we have launched and we have operated, and we know how to do things, and we have the laboratory as well. So I'm heading this mission of a 1 meter class called INSIST. It's a UV optical mission, and this is the Galaxy, and UVIT actually could resolve it, and we think it can be much better resolution. So I can go into the technical details later, but this is something we are working on. So I am heading this mission. This is still in the preparatory phase. Now what I'm doing with JWST, you would have the Stefan quintet image from HST, and JWST has made a lot of, you can see this is the HST image. This is from the HST, but you would have seen this high five image, right? It's a very popular image. So this is high five, but then you can see the velocities of this written here. This is 6,700, this is 5,700, 6,600, and 6,600. On the other hand, this is 791. So this is how astronomers say that if you have seen 5 galaxies, are they together? Are they all together? No. They're moving with different velocities. So of this, these 4 are together, this is not together. Now, these 4 are interacting. This is quite far away, but these may be interacting with each other. So this is how people start understanding the interaction between galaxies and what happens if galaxies interact. What is the aftermath? So what we have done is, this is the combined image of JWST and UVIT in 3 filters. And in this case, if you can focus it on here, you can see that one of the JWST filters is yellow. But we have given UV image color. This is from our UV telescope, there's AstroSat image in blue. You can see that this galaxy, which was actually not part of it, like 790 kilometers, has a lot of UV emission, signifying that there are a lot of young stars. But here, none of them have young stars. If they had young stars, we would have picked it up. But you can see that the emission is all around it. And if you go and look at the JWST image in the pH, one of the filters I indicated that the polyaromatic hydrocarbon. So it's basically the pH molecule. It is tracing the molecule. So the UV, we believe that the ultraviolet is exciting the molecule out there. And a large number of molecules are sitting there. So this is the work we have done recently, and as you can see, n number of papers are submitted, so we have also written it up and submitted for publication. So yeah, so what's next to Webb? Now, this is the technology now we have demonstrated, or the world has demonstrated, to take multi-mirror telescope in space. That's a completely new, different technology. Now, you have demonstrated it, you have skill set developed, you have techniques developed, you can't let it die. So any project for that matter, it goes to the next step. So they are planning to have a bigger LUVAR telescope, but what will launch it? Because you also need a rocket which can lift the entire thing up and put it in orbit. So probably this will be the next generation, but it will be somewhere in 2030s or 2040s. So that is one thing which is happening there, and actually people have been looking at which is your favorite object in this. So if you look at the tweet, people say, which is my favorite object is this. So like that. So it's basically stretching which is happening, which is because of the background galaxy, and this is actually beyond that. So you get the series. You also see groups of galaxies out here, and these may be clusters. So you have galaxy groups. So galaxies are actually found in groups, and you can have voids between these groups. So empty space and groups of galaxies and empty space. So we think that they're kind of, in a connected together, and there are empty space between them. So these are groups of galaxies, but you see them over together, but then you need to get their velocity estimations to figure out groups of galaxies. And there are umpteen galaxies which are very, very far away. So you can see this particular red thing. This is really, really far away. So they are at very high redshift. So one can actually, if you measure all the distances to everything, you can actually slice it up and find out, as you go past a certain look back in time, what is the density of galaxies. I understand that this 25 here, 50 here, maybe 25 here, 30 here. Now, how do they appear to be? What is their morphology? Are they forming stars? Are they looking spirals? What kind of things are happening there? So the papers which I showed are already looking at statistics. If I look back time, I slice it out here, what is the density here? If I slice it out here, what is the density here? And what are their properties? So this is the kind of studies you can do right across. And of course, the color tells you what is the kind of material present in them. Is it gas-rich, dust-rich, star-rich? So we know that as the time changes, the rate at which the gas was converted to stars changed. We don't know why, and we know that there is a peak. What drove that conversion from gas to stars, we need to understand. So those kind of things can be done, and these are the kind of things you can see. Some are having spirals. Probably it is a closer nearby one. But as you look back, the features are pretty, you can't clearly define the features. And there are many galaxies which probably are interacting here. As you can see the connections between the two, which would mean that the material is being stripped and then falling down, etc. Does it answer your question?
Yes, thank you so much.
This thing, right? So you have a cluster of galaxies out here. So here you have a lot of dark matter sitting here, which is not emitting. So if you want to find out the total mass of this particular cluster of galaxy, you cannot image the light and convert the light into matter. There are a lot of matter which is not emitting light. So if there is gravitational lens happening here, that will tell you how much matter is required for it to bend that much. Okay. So that actually gives you an indirect estimation of the amount of mass within, which also relates to the dark matter. Okay. So that's all. Thank you for your attention.